schemes, you can do any one. But I prefer that it should not happen that all of you do only that. So try not doing a problem different from your other friends. Okay, so then let me start. Is my screen visible? Hello?
Yes,
Is
sir.
okay.
Yes, sir, it's visible.
Okay. So last class, actually I discussed overall how to evaluate stresses. So today I am first going to discuss overall solution, how it will proceed. So let me continue with this. Elastoplastic analysis. So I am going to discuss the overall algorithm. So first, you already know that from kt into delta d is equal to f, you get delta d, and then you can get the element level incremental displacement vector, and from there you can calculate the incremental strain at a gas point in an element. So that I am taking as a given information. So now this you have to do at every gas point of each element. So at a gas point, B no or B are given. So I have already told you how to get that. So see, we know the delta epsilon and the state, and the state would be in the form of a status variable. So either status is equal to elastic, that means in the previous iteration the point was elastic, or plastic. So this would be this information would be given. Delta epsilon state would be given from the previous step or iteration, and from the previous step or iteration we will know the stress, we will know the plastic work, and we will also know the back stress. So these informations are coming from either the previous last iteration of the previous load step or the previous iteration of the current load step. So you will get this information. Then you calculate the elastic predictor stress delta S, which is simply assuming that the entire strain step is elastic. So you calculate it as delta epsilon. This is elastic predictor. And then you calculate the trial stress, which may not be the correct stress, but so we are saying it as a trial. Sigma trial will be equal to sigma naught plus delta S. This is intermediate trial stress. So then now, so once we have done this, the initial set of calculations, then we evaluate yield function. Now evaluate yield function. So again, only stress we are using trial stress, and other quantities in the yield function are corresponding to the previous iteration or step. So basically we evaluate here f, which is a function of this sigma trial, and other quantities are taken corresponding to the previous step or iteration. So once we calculate this, then there are two possibilities. One is if the previous status was elastic, So now you have to store these variables at every gas point of each element. So then only now you can get these. So if the previous status was elastic, at the given gas point, at the particular gas point, at a particular gas point, so once we know the previous step, previously the gas point was elastic, there was no elastoplastic deformation in that. So now there can be two possibilities again in this. So number one is that when you calculate this F sigma trial, so this comes out as either less than or equal to 0. So previously the point was elastic, and currently also when we evaluate the yield function, so either that is less than 0 or equal to 0. So this means that from the previous step to the current step, the entire step is actually elastic. So then the trial stress is a correct stress increment. The entire step is elastic. And if this is so, so then the correct or the new stress for the current step, you can take the stress for the current step as, I am denoting that as sigma new, which will be equal to sigma trial, and this will be at that gas point, this is going to be the correct stress. So that is one possibility. Second is there can be transition from elastic to elastoplastic. So then the other possibility is that sigma f of sigma trial may come out to be greater than 0. So if it is greater than 0, then that means the step is elastoplastic. The step is elastoplastic. And in this also, now there are two things, because previously the point was elastic and now it is f is coming out to be greater than 0. Why it is coming greater than 0? Because we are keeping the yield stress same what was there, the initial yield stress. So that is why, and now the state of stress is greater, so this f comes out to be greater than 0. So we have to actually evaluate the elastoplastic is the stress in stress increment. So now the possibility, like if I take a 2D state of stress, so if you have this sigma 1 and sigma 2, and then let us say this is your initial yield surface, this is the initial yield surface, and initially the previous step the point was somewhere here, and now since f is coming out greater than 0, so that means now the one new point is predicted over there. So now from here to here, so if we take say this portion as beta and this portion as 1 minus beta, so then we need to calculate beta, that is how what part of the step is elastic and what part of the step is elastoplastic. So we need to calculate beta. So that is how do we calculate? So by taking the just coming to this point, and that point is where f is just equal to 0. So you calculate f of beta, which would be calculated as f of sigma naught plus beta times delta s. So you calculate this and equate it to 0. So from this you can find beta. Using Noether-Raphson method, you can find beta from this expression. And once you have found out beta, then you have an intermediate new stress. So that is, let us say, I denote as sigma dash nu. So sigma dash nu would be sigma naught plus beta times delta S once you have calculated beta. But for this particular load step, there is still the strain 1 minus beta times delta epsilon. So for 1 minus beta times delta epsilon, this strain step, for 1 minus beta delta epsilon strain step, you need to calculate delta sigma, and you will calculate delta sigma as we discussed in the previous lecture. That is, you express all the stresses in terms of delta epsilon equivalent P, solve for delta epsilon equivalent P, and then get the incremental stresses. So you need to do that, and then the final no stress after the this particular iteration would be sigma nu is equal to sigma dash nu plus delta sigma. So you will so this is one possibility, that after doing this initial set of predictor calculation, that is basically, after calculating this, then we calculate if the previously the point was is elastic. So if it was elastic, so we then have the possibilities either no one or possibility number two. And second is could be that if the previous step was elastoplastic. Now the if the previous step at that particular gas point, we are saying, so if the previous step was elastoplastic, so that means that would be indicated by this status variable as plastic. So you can, like, use one for elastic, two for plastic, like that you can store this status variable, and then you can always check. So now if this is the case, so again, if the previously the point was step was elastoplastic, so if it was elastoplastic, so if I again represent in a 2D two-dimensional state of stress, so there would be, let us say, this is the initial yield surface, and since the point was previously elastoplastic, I am demonstrating through the kinematic hardening. So now if you look at, this is the initial yield surface, and this is the the previous step yield surface.
Sir, actually it is isotropic hardening, na?
Yeah, this I am demonstrating for isotropic hardening. So now the previous, suppose we were somewhere here, and now the current, when we calculate the incremental stress, and that is the for the current step, so we are going, either possibility is that we go in this direction, which is loading, or there can be unloading. There are two possibilities again. So this is loading, that means the elastoplastic loading is continuing. So that is one possibility, or there can be unloading. So these are two things which can actually happen in this. So then how do we check that whether it is loading or unloading? So you need to for checking that, if we look at f evaluated at the current trial stress, so the current trial stress would be this sigma naught plus delta S. Delta S is elastic predictor. So when we calculate this, so if we use Taylor series and take first two terms, so we can write this as f of sigma naught and plus del f by del sigma transpose into delta S. And now suppose this f, this difference is greater than 0. So that means del f by del sigma transpose into delta S would be greater than 0. So that means you can write f of sigma naught plus delta s minus f of sigma naught. This would be given by del f by del sigma transpose into delta s. So you need not evaluate these two. You can just do the calculation based on this del f by del sigma transpose into delta s. So if this is greater than 0, that means f in the new trial stress is greater than f in the previous step, so that means it is actually loading. And if this is less than 0, then it is unloading. So we can just check the del f by del sigma. We calculate del f by del sigma from the based on the stresses calculated in the previous step, and delta s is the elastic trial stress increment has already been calculated. So then you check this product, and if this product is greater than 0, then it is the elastoplastic loading. And if del f by del sigma transpose into delta s is less than 0, then it is elastic unloading. So there are two possibilities. One is, as I said, del f by del sigma transpose into delta s. This is greater than equal to 0. So then means the delta s direction, the trial stress direction is an ascent direction. That means loading is an ascent direction. That means there is a loading. I already explained. So that is one. And no r, you could find that del f by del sigma transpose into delta s, and these are easily calculated quantities greater than 0. So that means basically this delta s is a descent direction, is the yield function is decreasing in that direction, is a descent direction. That means no, the unloading is taking place. So now how do we do that? No, there are again no, if you look at the we'll have to take care of both the situations. So if no, the previously the point was elastoplastic,
Sir,
and del f by del sigma transpose into delta s is greater than 0, greater than equal to 0, then that step is elastoplastic. We calculate delta sigma and then update the stress. Yes, please.
Hello. Yes, sir. Sir, this
Yeah,
delta S, like this is the
yeah.
change in stress, right? Uh,
Yeah, this is actually elastic predictor. So as I said at the beginning, no, for after solving for delta D, the incremental displacement, we calculate the incremental strain for the element at a particular gas point, and then calculate this. So here this is elastic predictor. We are assuming that this entire strain step is elastic, and then we are calculating this incremental stress.
okay.
So
So
it may
my
not
doubt
be correct.
is,
Yeah,
yes, sir. So my doubt is like we at last we have written del F by del sigma transpose into delta S
yeah,
greater than equal to 0, and
yeah,
then we are telling that delta is S is the ascent direction.
yeah.
But sir, like how do we know that del F by del sigma cannot be negative? Like suppose if both of them are negative, then also the product will be greater than equal to 0,
So
sir.
yeah, so that we are checking from both actually, no. So whether no, it is, if it is greater than equal to 0, that is one possibility, and the other possibility is that it is less than 0. These are the two possibilities. Now the some components of del F by del sigma may be positive or negative. It doesn't matter. The possibilities would still be only two: either del F by del sigma transpose into delta s is greater than equal to 0, or it is less than 0. So these will be the only two possibilities, although the individual components of del F by del sigma and del s could be positive or negative.
Okay, sir.
Yeah,
And sir, one more thing, so here we have written if the previous step was elastoplastic.
yeah,
So, sir, like while implementing this thing in code, like
yeah.
how will we deal with this? Like
So you
there,
have
like we
you
both.
have to have an no, barrier array which will be the dimensions of that array would be the number of elements, it is a two-dimensional array, and one is number of elements, another is number of gas points at each element, and then you will store either say one for the elastic and two for the elastoplastic. So every time when you do the calculation, you are going to update that variable, that whether now the gas point is elastic or elastoplastic. Initially, of course, the all gas points would be elastic when you start increasing the loading. So initially all points will be elastic. So you will say denote the status variable as one for all the gas points, all the elements, and subsequently based on this analysis, you will be updating it. When it is
Okay.
crossing the initial yield surface, then the status of that gas point would change from elastic to elastoplastic. So you have to store, you will have to store all these variables. You have to store stress at all the components of stress at all gas points of each element. You have to store this status variable. You have to store this elastoplastic, the plastic strain, epsilon equivalent P has to be stored. You have to store the plastic work. You have to store the back stress. So all those quantities have to be stored. So now compared to an elastic analysis, you have to store so many variables, so that now you can use now from the previous step or previous iteration, you have those values available, and then you can update them.
Okay, sir.
Yeah. So now see, these two possibilities are there. So now the one is, if del f by del sigma transpose into delta s, if this is greater than equal to 0, that means what we are saying, that it is loading. So then you calculate delta sigma. I have already told you know how to get this delta sigma for elastoplastic case. Know that we express all the stress increments in terms of epsilon, delta epsilon equivalent P, then solve for delta epsilon equivalent P, and then get delta sigma. So you'll have to calculate delta sigma, as already explained in lecture number 18, and then you have this sigma nu. The new stress at that gas point would be the previous stress plus this delta sigma. So this is if it is actually continued elastoplastic loading, and within this there is a second possibility, that no if del f by del sigma transpose into delta s, if this is less than 0, so then this is elastic unloading. This is elastic unloading, and so now again there are two within this elastic unloading. Again there can be two situations. So let me again show through the two-dimensional this yield surface for isotropic hardening case. So let us say we have sigma 1 and we have sigma 2, and then we have the initial yield surface and the yield surface of the previous iteration. So when you are unloading means you are moving inside this yield surface, the current yield surface. So you are suppose coming from somewhere here to here. So that is one possibility. So you are remaining within the previous step yield surface. That is one. And if this is the case, so then you can see the entire step is elastic unloading, and then you can calculate sigma nu, that is the current stress for the stress for the current step as sigma naught plus delta s, or no, it is simply equal to trial stress. But the other possibility is that it is unloading, but the other direction, which is no, most of the time it is unlikely because you will take smaller steps, but any that possibility can be there. So the second thing is that no, when we look at sigma 1 and sigma 2, and this is the initial yield surface, and then this is the previous step yield surface, and you were here in the previous step, and then when you are going, it is crossing and going somewhere here. So if it is crossing, so then this part of the strain is, let us say, beta times delta epsilon, and this part of the strain from here to here, it is 1 minus beta times delta epsilon. This is similar to what we talked about. No, the previously the point was elastic and now it is undergoing elastoplastic. So that kind of a situation may arise. So now in this case, if the first possibility this is there, no, you straight away you calculate no your current stress from this formula. But if this kind of a situation is there, that in from the other direction, no, in that direction when you are moving, your load is such that again it is crossing the previous step yield surface at the other point. So part of it means elastic unloading, and then part of it is elastoplastic kind of you can say again loading. So part of it is partially elastic unloading and part of it is elastoplastic loading. When the further plastic deformation is taking place, we are taking that as elastoplastic loading. That is this part. So now for this you have to find beta, and that is the same way the way we already discussed. So we will find beta so such a way that the yield surface, you are moving inside this previous step yield surface. So up to this point the yield stress is going to remain same. Yield stress will not change. Whatever was there in the previous step, the same yield stress would be there. So now you will have F, which is in terms of sigma naught plus beta times delta S, and the other parameters, no, the W naught will be from the previous step, the plastic work, and if you are kinematic hardening, then this sigma alpha back stress that also will not change up to this point, because no the no the plastic strengths are not changing. So this is equal to 0. So from this, again using Newton-Raphson method, you can find out beta. And once you find beta, then you can calculate the intermediate stress. Intermediate stress sigma dash. I'm denoting that as sigma dash. So sigma dash nu you can calculate. That would be sigma naught times beta into delta S. We will calculate this. And for the remaining 1 minus beta into delta epsilon step, you will calculate delta sigma as explained in lecture number 18. So for remaining strain increment, that is 1 minus beta into delta epsilon. Calculate delta sigma. The way we explained already in the lecture 18, and then you update the stress. So finally the stress at that gas point is going to be sigma nu, which is sigma dash nu plus delta sigma. So this is how now you will continue the calculations. So now, so this was the overall algorithm. You see, at each gas point, you have to store these variables and you have to do these things. So let me just summarize. So if you look at the complete set of equations, the summary, if I look at, so So if you look at the complete set of equations we deal with in plasticity, in addition to the global no iteration equation kT delta D equal to F. So in addition to that, the complete set of equations which we deal with is quantity lambda, which is D of epsilon equivalent P, and this is given by, we have already derived this formula, 1 upon A del f by del sigma transpose. We have derived this. So the same quantity I am writing here, delta epsilon, and for no this A is del f by del sigma transpose into CE into del Q by del sigma. Q is the plastic potential function. For associative flow rule, Q would be equal to F minus del F by del WP into sigma transpose into del q by del sigma and minus c into del f by del alpha. So these equations I am writing for the general case. That is, they either can be, there can be, kinematic hardening, or they can be isotropic hardening. So if the isotropic hardening is there, the third term will not be there, and if kinematic hardening is there, then second term will not be there, third will be there. So this is del q by del sigma. So this is how you calculate this, the expression for delta epsilon equivalent p. And of course, because this is in terms of sigma, so we already know that how to calculate delta epsilon equivalent p for elastoplastic step. And then the quantity increment in the plastic strain tensor will be equal to lambda, which is delta epsilon equivalent p into del q by del sigma. So this is your flow rule. And then the plastic work, increment in the plastic work, this formula also we have derived. So that is rather defined, d of epsilon p. And then d alpha, the increment in the back stress, we have seen that using Prager's rule, which is simplest kinematic hardening law. There are more complex kinematic hardening laws. So this is equal to this now we calculate d alpha increment in the back stress using this formula. And then we know that d of sigma is equal to elastic constitutive matrix C into, we have d of epsilon minus d of epsilon p. Where now we have already said, no, this C is coming, that is elastic constitutive matrix. So these are the kind of equations you are dealing with within the elastoplastic analysis. So this is just a kind of summary. Uh, now there are simpler approaches also for solving this elastoplasticity problem. So the approach which I discussed for the elastoplastic loading, this calculation of delta sigma, that is referred to as return mapping, the approach. So let me say write that. So the approach discussed for evaluating this delta sigma, that is done in lecture 18, is known as return mapping. Why it is return mapping? Because you are initially elastic predictor, you are going somewhere outside the yield surface, then you are updating the yield surface and coming back on the yield surface. So that is why it is referred to as return mapping. Now there is a simpler approach to calculate the stresses, that is known as the forward Euler integration, which is an explicit technique. So let me also tell you how to do the using this technique. So one is, we have already discussed based on lecture 18, and Quater algorithm I have discussed. So you can actually do the calculation based on that. There is another approach, so which is known as forward Euler integration. And this is explicit, it's not an implicit technique. So obviously the uh, the condition that your annealed surface may not be satisfied in this technique. So for solving this, using this forward Euler integration technique, so this is an alternative approach. Just now whatever I had discussed, it is alternative to that. So now in the forward Euler integration scheme, again we will know the solution from previous load step. we will know, let us say the stress at from the previous load step, we will know the total strain from the previous step, we will know the plastic strain from the previous step, we will know the plastic work of stresses from the previous step, we will know the back stress from the previous step. So these will be known. Also we can calculate at the previous step the gradients. So the gradients are like del F by del sigma from the previous step, del F by del WP from the previous step, del F by del alpha from the previous step, and del Q by del sigma from the previous step. So all these are calculated from the previous step, and we have some strain increment from Kt delta D equal to F. We would have calculated delta D, then extracted for a particular element delta DE, and from that we would calculate delta epsilon at a particular gas point. This has to be done again at every gas point. So from this we know the strain increment. Strain increment, now we are dividing into a number of sub steps. So say delta E is equal to delta epsilon divided by n, and here no, the n is number of, we have one load step, and then within that we have a number of sub steps. So n is number of sub steps. Then now within this load step, we do loop over all the sub steps, that is n sub steps. So that means for each sub increment, let us say that is n plus 1, and where n is going from n is equal to 1 to n in the step of 1. N I have already defined. This you have to choose. Now in your program this has to come as an input. So you will calculate. Now these are the calculations. I will show you all the calculations. These are based on the summary of equations I have already given you. So then you calculate the total strain for the current sub step. So total strain would be epsilon at n plus 1 will be epsilon n into delta E. This is a strain increment per sub step. Then you calculate the plastic multiplier, that is lambda or delta epsilon equivalent. Plastic multiplier, let us say call that as lambda. So this lambda, now this lambda you will calculate as basically based on the the previous information. So I am denoting it as delta epsilon equivalent P at the nth step, which is 1 upon an, a, that same a, del f by del sigma calculated based on the previous step into ce into delta e. That's the strain increment, and where this an is again the same formula, del f by del sigma transpose at the previous sub step into ce into del q by del sigma calculated at the previous sub step. Now I'm talking about sub steps, minus del f by del wp calculated at the del f by del wp calculated at the previous sub step into sigma calculated at the previous sub step, sigma n transpose into del q by del sigma calculated at the previous sub step, minus small c into del f by del alpha calculated at the previous sub step into L into del q by del sigma n. So yeah, so you calculate this and then update the stress. So then you will be updating stress. So when you look at the stresses, so sigma for the current sub step n plus 1 will be equal to sigma for the previous sub step sigma n plus ce into delta E minus lambda n times del q by del sigma calculated at the previous step. So this is how you update the stress, and then you also update the plastic strain. So plastic strains are updated as epsilon p at the current substep, that is n plus. This is substep. Now the load is, now you keep in mind that this n is substep. You will have, this is part of a particular load step where you increment the load. So this is, the plastic strain will be equal to epsilon p in the previous substep plus lambda n we have calculated, and del q by del sigma n. And then you update also the back stress and the plastic work. So back stress is equal to alpha at the current substep is equal to alpha in the previous substep, and plus the c into lambda n into del q by del sigma n. C into lambda, no, I think I missed something. So alpha is alpha n is equal to c into lambda n into L is there. No, here you have to have this L. So c into lambda n into L, and then you have this del q by del sigma from the previous substep. And then lastly, you also update the plastic work WP. So the plastic work for the current substep will be equal to plastic work in the previous substep plus lambda n into sigma n transpose into del q by del sigma n. So in the this is actually explicit technique. So you may drift away from the yield surface. So the accuracy would depend on how many sub steps you are taking within each load step. But it is a straightforward calculation. You would see that this is fairly straightforward if you are doing that. So the advantage is that it is straightforward. Programming efforts are very minimal in this. Whereas the return mapping approach we use, which is a implicit technique, that is program. The lot of programming is needed, so that is much more complex. But that ensures that you are on the yield surface, whereas this does not do that. So the accuracy here is highly dependent on what you choose as the capital N, the number of sub steps within a given load step. Yeah, so I think this is what I wanted to discuss on elastoplasticity, although this itself is a subject in itself. But I think in uh, a few lectures I have tried to give the basic essence of elastoplastic analysis using finite elements, how to do that. Although no, you can find the books on the computational plasticity and like that. So like 1,000 pages books, 500 pages books on computational elastoplasticity. So this is a very brief I have now given here. So the next topic I'm going to start is the viscoelasticity. So yeah, so now this next topic is viscoelasticity. So this is basically in the elasticity it accounts for the strain rate effects. So this accounts for strain rate, sensitivity, of material. And viscoelasticity is important when the material is near glass transition temperatures. So many of the polymers, elastomers, glass transition temperature is near the room temperature, so they behave as viscoelastic materials. So this viscoelasticity is a behavior of material near glass transition temperature. Near glass transition temperature, and let me denote it by Tg, the glass transition temperature. And what is what is so specific about the glass transition temperature? So glass transition temperature, I have denoted it by Tg. So in near the glass, if there is a small change in the temperature near glass transition temperature, so there is a significant change in the viscosity of material. So viscosity of material changes significantly uh, it changes significantly due to change in molecular structure. So yeah, now this is now depending on compared to glass transition temperature, what is the operating temperature of the material. So let's say that the operating temperature of the material is T. So let the material temperature be T. So if the material temperature is T, one possibility is that T is less than Tg. So if the temperature of the material is less than its glass transition temperature, then it will behave as a solid. And now if T is approximately equal to glass transition temperature, then the shear modulus is low, and material shows sensitivity to strain rate. Now the third thing is that the temperature is greater than glass transition temperature. So T is greater than Tg. In this, the behavior is hyperelastic, and the sensitivity to strain rate is minimal. So behavior is hyperelastic. So that means it undergoes elastic deformation to up to very large strains, 200%, 300%, 400%, and like that. So it's a hyperelastic and a minimal sensitivity to strain rate. Yeah, so this is basically you can from this you can understand that when to use viscoelastic constitutive model in your finite element analysis. So if the are hyperelastic if the temperature is greater than glass transition temperature, but if you are close to glass transition temperature, then the strain rate effects would be significant, and you have to model the material as viscoelastic material, at least viscoelastic. The other complications can be viscoplasticity and so on, but we are right now talking about viscoelasticity. And in viscoelasticity there are two main phenomena. which happen. One is stress relaxation, another is known as creep. So stress relaxation. So in stress relaxation, what happens? Suppose you take a uniaxial sample and stretch, apply a constant strain to that. So this side is time t, and the vertical axis is the strain axis. So the strain is constant in this. The strain is kept constant. To study the stress relaxation behavior, the strain is kept constant. So the strain is constant. But when you look at the stress, when you look at the stress, so again this side is time t and this side is sigma x. So if it is a elastic material, so if strain is constant, stress will also be constant. But in a viscoelastic material, there is a stress relaxation. That is, within time the stress is reducing if we are keeping the strain constant. So the stress would it would be a non exponential curve. It is not a straight line. So it would be like this, and this is the initial stress, say sigma xx naught, and this is how it would decay with time. So this phenomena is known as stress relaxation. Then the other phenomena in viscoelasticity is creep. In creep, what happens now? Now the stress relaxation we keep strain constant and stress is decreasing with time. In creep we keep stress constant and then strain increases with time. So that is known as creep at a constant stress. So now you have this sigma xx and this side is time t. You are having a constant stress sigma xx, but when you look at the strain, so this side you have epsilon xx and time again, time t. So if you look at the strain initially, of course, there would be, when you apply the stress, there would be some strain due to elastic deformation, but then due to viscoelasticity, viscous effects, restraint rate effects, the strain keeps on increasing with time. So that will be, again something like this. So this is the creep, and this is the initial epsilon xx naught, initial stress. So yeah, basically you will find that we have to model when we want to use a particular constitutive relation for viscoelasticity. Our aim is to accurately predict the stress relaxation and creep. So these are the phenomena which we will need to model accurately in the viscoelastic analysis of a material. So I think this is where I want to stop, and if you have any doubts and questions, you can ask. Yes, anybody, any doubt, any question?
Sir, for finding beta, what will be the initial guess?
How to find beta? What will be
Initial guess.
initial guess? You can take it as unity. Initial guess either can be unity or zero. I no, yeah, I think even 0.5 also may be okay. So either 0.5 or unity.
Okay, sir. So it will be between 0 and 1.
Yeah, it will be. Of course, beta is going to be between 0 and 1. Yeah, so the 0 means basically the entire step is elastoplastic, and 1 means the entire step is elastic.
Okay, sir.
Yeah. Anybody, any other question? Okay, so if there are no questions, I am stopping. Thank you all for your attention.
Thank you, sir.